All right, thank you everyone for coming. You're not going to be disappointed. You're missing games and beautiful day outside to hear about physics. So it's I think it's about what the talks are about what's passionate, what I'm passionate about, and it may be a bit hard to understand why I would be passionate about such a subject. So I'm going to try to explain to you the great stuff about it and what I felt. It's a physician said it's both beautiful and useful. So very rare combination. And I think more than that, it really defines the world. Carl Sagan said, "We are the universe trying to make sense of itself." And that's something that I find quite touching. We're, without us, without thoughts, without the language, without humans, there's nothing out there. And we make it happen. We make it happen using our knowledge and using physics and using the experiments. So all of it really opens up possibilities, and what physics is really really opening up the possibilities of what the world is and what the world can become. And if you look at the history of physicians, the new theories have been linked with new theories. New way of thinking have been linked to new findings. So it's really a big opportunity for all of us to change the world. And just as interestingly, it's actually open to everyone. Changing the world, changing the way we perceive things, changing what it is means you kind of have to be a bit outside the system. You have to be thinking a bit differently. And you'll often find that great physicists, people who've changed things radically, were a bit, not only a bit different, but really were using common sense. They were just like you and me. We tend to deify them for whatever reason, but really they were very often people who were taking some very simple concepts or some very simple experiments, some very simple observations, and saying, you know what, that doesn't quite fit with the grand theories. And I find that very exciting. I find that really close to my ideas of I think what we all share, the democracy, the fact that we can all make a difference. So that's kind of the basic layer, the basic foundation of what I find interesting about it and the great things about it. Now, a couple of things to add to it. There's also the kind of like the far out aspects to it. I mean, once you look at the findings and once you look at the theories, it's it's pretty far out. You know, you learn things like about the universe expanding, things growing. We are all expanding. You are familiar with it. If you look at stars that are far away glow at a different rate, a different light wavelength than far that are closer. And the only explanation we can come with is that, well, they're moving away from us. And that happens wherever you're in the universe. It's not like we're the center. And from there we deduce that, well, the universe is expanding. It's not we're moving away. No. The very fabric of the universe is getting bigger. So that's kind of like one of the far aspects. You're not here. I don't mean because you're not paying attention because you're eating. I mean, you're not really here. Every one of your particle disappears and gets back together. We're all made of waves and particles. That's kind of like the far out things that make you say, wow. I used to write programs for fractals and start talking to potheads in school because, you know, they liked it. Other students were like, what are you talking about? Or like, say, yeah, no, they liked it. And there's this far out aspect to it that I don't know, I find very, very disturbing and attractive. The fact that we've done experiments that show that a particle interacts with itself. I'll get back to it a little bit more, but I think you all have heard about this type of kind of far out experiments. And beyond those type of very point and tricky experiments, I think there really is a link to the great philosophers. I talked a bit about it, but Galileo and Socrates and how our way of thinking really depends on it. So in philosophy class we talked about Socrates, and there was a very famous debate he had Protagoras, and in there an open question was is there an absolute truth or not? And very quickly Socrates, being very good at finding contradiction, made fun of the guy, saying, well, oh, so there's no absolute truth? No, there's no absolute truth. Oh, so what you're saying is not true. It's not true absolutely. And he found a contradiction. And I think what was happening at the time is the physical world and the understanding of the physical world was such that they didn't have the tools and the understanding to kind of counter it and move to a more relativistic point of view. The absolute rule we now know is not true, but at the time there were many relativists who also believed they weren't true, but they didn't have the tools and the physical experience to prove it. And so they didn't develop the mathematical tools they needed to counter it, the set theories that links the truth to a set and to a context. They didn't have all of that. So instead, what we had developed are very monolithic system of beliefs, right? You looked at the universe, it's stable, you have the earth, you have the sky, you have the earth, and so you had this monolithic beliefs with gods and monotheist beliefs that came out of it. And later on, you had one great thinker, Galileo, who was really the first one to break that mold. He's the first one who started talking about frame of references, and it completely changed the way people thought. We often associate relativity to Einstein. In fact, many people have talked about it before, and Galileo is the one really who put it forth and said it concretely in the physical world. He talked about how when you drop something from a moving sailboat from someone in the boat, it drops straight, but someone out in the river, he may see it dropping at a curve, and he started talking about falling object and gravity and frame of reference. In fact, if any of you have taken physics in school, Newtonian physics, when you derive anything in Newtonian physics, you're looking for a Galilean frame of reference, something that basically is not accelerating. He did that by actually kind of a very simple observation. He developed his great breakthrough technically was to develop a telescope that saw better, further. He didn't do a telescope, he improved it, and with that he was able to see the movement of stars. And that's what he did. He basically worked at the observatory and checked things out, and he saw that things weren't really moving around Earth. He saw that Mars, for example, depending on how Earth was in position to Mars's orbit, was sometimes moving in one way, going back and moving back again. And that didn't fit with the Earth being the center of the universe, so by simple observation, he said that doesn't quite fit, and he developed the theory that, well, maybe we're not at the center of the universe. And that completely broke our way of thinking. So we could not think after Galileo like we thought before. Having this type of evidence changes everything and changes really the world itself. I'll give another example that maybe not as famous. Spinoza. He's a great philosopher. He was also a physicist, and he worked on Descartes' work, and he was used by Marxists. I don't think Marx would have been able to develop a theory of materialism without going back to what Spinoza was writing and really putting matter at the essence of things. Mm-hmm. The physics and the interpretation of physics really changes everything, changes how we think. And Spinoza is another case who was just completely, outside the system. I think he was grew up to be a rabbi and then was kicked out of the community because starting to think of matter as cause of everything, as cause of itself, which is typically reserved for God, wasn't very well seen at that time. There are many other examples you can think of. Newton. I like Darwin a lot because I agree with Dawkins. Darwin there's a before and there's an after. And he's not a physicist, so he doesn't quite fit in there. But you can see that after evolution, you cannot think of life. You cannot think of anything the way it did before. And it's taken hold, and it has influenced how people think about economics. It has influenced how many people, think about even social relationship. We actually tend to take it too far sometimes and and have those findings and move them into the social organization, which doesn't always make sense, but that's how we are. We make the world from the physics and from our understanding of it. And so that's why physics is so important. It really will define everything and open up the gate for physicists, for philosophers. Philosophers have always relied on physics and define themselves as the scientists of science. They need something to work with, and in the end, you need to go back to the experiments. So that's what so that's hopefully, I've conveyed a bit of why it's interesting to me. One last point on Einstein. Einstein also great physicist, and he developed he pushed the frame of reference and the relativity a step further, and with his view, it went from having relativity from a frame of reference to relativity to a human being, and we start thinking about, well, human rights and that type of things. And I think both of them basically evolved from the same concept, the fact that we're breaking the frame of reference down to a lowest level. And he was also someone who was thinking outside the system. When he developed his theories, he was working at the patent office. He wasn't working in a big research lab, so it's very impressive. But that gave him the ability to think a bit differently and look at things. And to my point, you don't need to have this research. I think it's a misunderstanding in physics that you need to have this big mathematical background and work for years. They're very often very simple concepts that anyone can have. Having an experiment that changes the way you see things and proposing an alternative. So I'll talk a bit then about how my story with physics. Then I didn't do physics. I started quite young. I loved to burn ants as a kid. Looking at how light go on them. I lived in a third world country with a lot of flies, so I hated flies. We dissected them and tried to see how they worked. With my brother to have a good time. The roads were empty. We built fires and threw insecticide cans because we had a lot of insecticides because of all the flies and tried to see how much. We made a good theory, how far the waves would go. And then I moved back to France. We moved to the 12th floor. It was really great. We were able to throw stuff out, and we would time how long it would take to hit the floor. Big object, whether big objects fall faster than small objects, and what happens when they fall. So that was a lot of fun. Unfortunately, school very often kills that, because you get to school, at least in the beginning, and it becomes, well, okay, conservation of momentum and things like that. And it's okay, but you don't get the same fun as you get until you get to, at least until I got to basically end of high school and university, where we start talking about really, I thought, great subjects like space, what makes space, the fields that define where we are. And one thing I loved was the acceleration of particles. So that in there, I think it reminded me a bit of when we used to take big things and drop them from the 12th floor. What you do is you accelerate something, actually you accelerate everything as much as you can, and then hit them on something else and try to take a picture. So you have to take a lot of pictures, because chances that you get little electrons or protons to hit each other is very low. So you do a lot, you accelerate a lot of them and hope that they'll hit each other. And it's great. If you've never seen it, you can see on a picture what happens when they get hit and the trace they leave. And it's kind of like playing detective. You're like, oh right, look, this is going at that. I can see the arc here. The radius is r, so that's how much they're probably going. That's how fast they're going, and you can try to deduce the mass. And you see 3 particles, and with using the fact that, well, the momentum must be preserved, you figure out the sum of the masses. You get different equations, and then it's quite interesting. They're missing elements, and this is where you're like, well, we'll say it's a neutrino. This thing that you can't really see, it must be there because you don't. Something is missing. And you build up those kind of theories of like, what's there, what particles you've just well, we didn't rotate them, but what particle was just created and what was happening. So I thought it was absolutely fascinating. You check a picture, and if you wonder why people talk about antimatter, it's basically because you basically have something that is looking like an electron that has the mass electron that's rotating the other way, so it must be charged the other way, and so that. I found that quite interesting. So I took a bit of advanced classes in that area and started looking into relativity, and that I didn't find as interesting. At least it looked very mathematical, and also there were some very strange things in there where when I started asking questions or wondering, it was like, well, you have to flip a minus sign or you don't understand. And in my sense, when you get to that level, when people tell you, well, you don't quite understand, I think basically they're not explaining it right. So I kind of lost interest a bit, but I started having a discussion with my father, who happens to have a degree in physics. And we started some very interesting discussions on relativity. And that's basically the basis of a lot of this talk and a book he ended up writing and that ended up editing and translating. So, you know, kind of inspirational, the books of your parents. It's always quite big. You can, I brought a bunch for those who want to, more interested and want to read a bit more about it. So that really piqued my interest, and I thought there was maybe more to it than meets the eyes. And so after college, I joined a company, a startup. There were really 3 of us, and we published a CD-ROM because we thought it was going to change the world on the universe. We had at our disposal hours of tape from 13 great physicists. And we thought that the CD-ROMs were the future. It's going to be multimedia, is going to change everything. Yeah, so on that part we were wrong. I tried, I was going to bring them, but I couldn't, I wrote most of it and I couldn't make it play on my computer, so I spared you all. Very, very interesting stuff. And I think that comforted me in the fact that everything it's actually quite simple. The mathematics of it is, don't get me wrong, the mathematics of it is very complex, and physicists aren't mathematicians. A mathematician in my university who worked with Einstein, who was quite old German, told me that Einstein actually used mathematicians to help him. So it's really complex, and so that part is complicated. But the actual physics, what happens, it's very simple, and there's a reason why it's simple. When you're dealing with science, you have to have something that is reproducible, that is explainable, and you can't do that if you say, well, to have this experiment, you have to go there, twist, and maybe you do this, and the experiment has to be very simple. And if you go back to the experiment, you'll understand most of it, or all of it, and you'll understand what people are saying and the theory behind it. So what I'm going to do today, I'm going to go over a couple of experiments, and hopefully you'll see what I mean. And I'm going to lead you to, well, then why the theory of relativity was developed, and then why I think, you know, there are actually better ways of explaining those experiments. So that's the book, and that's one of the first experiments I'm going to talk about. Let me stop my notes here. Give me a second. So, here is one of the first experiments that I'm going to talk about. It's the light was not always thought as being something that takes time to travel, right? So it used to be think like if you turn on the light, it looks like it immediately appears. And someone, a Danish physicist, looking at the moon around Jupiter, realized that there's something consistent to it. When it starts going behind Jupiter, right, it was able to measure how long it takes for it to from the eclipse to start to when it's fully behind the Jupiter, as well as when it starts going out of the eclipse and come in full view. And you expect something fairly consistent. But he saw some inconsistency. Basically, you know, when the moon is receding, because it's going away, it's going to take a bit longer than when it's coming back to you. And he was able to deduce from it that light takes some time to come. Right? Does that Does that make sense? Basically, if light starts from one point, and at the end, it's going to take a bit longer than the last event you have. And that's relatively simple. But that was a very simple experiment, someone looking at the moon, one moon, and figuring out, okay, light must take some time to come. Now, some other very interesting experiment. First, I'll talk about waves a bit. So light not only has finite speed, but also is understood as kind of like a particle. You can see light being absorbed, which sounds like it's kind of like a bullet. You've all heard about the photon. Now, on the other hand, there are some properties which is called interference. So, if you take two balls and drop them in water, they'll each make waves. And this picture hopefully will demonstrate what I see or what I mean about inference. So here you have two balls, right? They're making waves, and the waves are moving. And where the waves meet up, you have a maxima. It's big. Where the waves where the bottom of the waves meet, you have a hole, right? You can play it on your bathtub. So that's a very, very specific property to waves. And very strangely, light exhibits this exact same property. If you have a light source, that's actually an experiment. You can buy a little infrared at a toy store to view it. By having two thin slots, a light source, you can actually see on the other side of the screen how exactly the same way as waves have minimum and maximums, light will show very bright areas and very dark areas, as if they're moving together in waves, and where the waves are up they meet, and where the waves are down they show dark. That's an actual picture of exactly that. So this is a picture of a black box with two slots. G3 is 1 and then 2, but it's the same idea. And this is what you see at the end. You can build it yourself and see it. You'll see a very bright spot, and then dark, and then bright, and then dark. That's not what you would expect if it was kind of like a bullet, right? If you start spraying bullet around, even if there's two people being sprayed, you kill everyone. You don't have like raw kill, still survive because I'm in the wave. So that's a very, very strange property of light. But it all goes to an experiment, right? You look at it, and then if you're depending on where the wave is, it's like it's up or down. Very strangely, the same thing we find with particles. So if you shoot an electron or a proton, a small particle through slots, you will find the same things. You will find that they'll aggregate into slides. And that's really weird, because here we're talking about matter. We're not talking about light, which we're like, well, maybe it was light, it propagates. No, here we're talking about matter. We're talking about us, the stuff that we're made of. The stuff that we're made of, when you shoot them, behaves exactly like a wave. You're not shooting bullets, because if you shot bullets through holes, you would see something very kind of uniform, or that would be big on some side and then degrading. No, we're not shooting bullets. We're not made of bullets. And that's really when you start talking about quantum physics and why we're waves and all the complicated things you hear about. It's this experiment. When you shoot things through little slots, you behave like waves. So don't worry, no one will shoot you through slots, or if you shot through slots, you wouldn't be like that. But the stuff you're made of is behaving very strangely. And even more strangely, this picture is one taken of one electron shot at a time from two slots like that, one at the same time. So in your mind, you have a wave, right? It goes through, but one electron at the same time, it's very hard to think about it as a wave. And yet, if you shoot it one at a time, this is what you see. And if you cover one of the slots, when you shoot one and cover the other slot, when you shoot the other, you will not see this. It's like the electron knows what in front of him is and interfering with himself. And when you hear people talk about, well, the fact that you can be at two places at the same time and that type of thing, they're really referring to the experiment. It's actually quite simple, even though people make a lot of it and the mathematics is not obvious. What they're saying is like, well, we've seen an experiment, and when I've been throwing stuff at it, it's like behaved in a very strange way, like this. So that's that is a couple of experiments that I found quite interesting. Now, I'm missing a picture. Okay, we'll do without it. So one more that was very interesting. So as we discovered those things, people start to try to make sense of the universe and try to think about, okay, how is it possibly made? Light is kind of acting like a wave or sometimes like a particle. So there must be something that light goes through, right? If it's a wave, something must be moving. So physicists of the 17th, 18th, and 19th century started coming up with the idea of the ether. How you say in English? Ether?
Ether.
The ether. Say, well, there's this ether that's everywhere. You can't really feel it, but it's there, it follows us, and that must be what's carrying light. We'll say that. I don't want to make too much fun of them, but that's, you know, they're trying to make sense of those experiments, and that's the best they could come up with. And a physicist called Michelson said, I'm going to prove that ether is there. And he built a machine that was able to pretty well calculate the speed of light. And it did that in two directions. And his idea was, well, I'm gonna go and look at light as Earth goes through the sun, as light coming through me. And via mirrors, I'm going to look at light going perpendicularly when it's not going through the direction of the Earth or even going behind it, right? And this way, if ether is there, I must be going through it. So light that's going to me, I should see that's coming faster than light that's coming from behind me, right? So he did that. He did this experiment, and he didn't find any such evidence. He found that actually the speed of light going, whether you come from here, whether you come from behind, from the side, was always going the same direction. Well, always going the same speed. So he thought like there must be something wrong. He went to the highest mountains he could find, thinking maybe air is like, you know, straying briefly. He was very, very determined, and he couldn't find any difference. And really, that's it. As far as the theory of relativity, that's the big one for speed. There are similar ones for the mass and why mass grows, but when you hear about Einstein theory, that is the main reason Einstein developed his theory. Light, whether you're going towards it or whether it's going towards you, you will see it, or away from you, you will see it coming at the same speed. So that was an earth-shattering experiment. And people started incorporating it into their theories. Lorentz actually is the first one who started talking about what could happen. And they started thinking about, some people said, well, maybe ether follows you as you're on. That didn't quite work. They started thinking about maybe things change as you gain speed. And this is where really Einstein theory took hold. And what he said was, well, I think the reason why you don't see a difference in the light speed is that when you move, the whole universe changes. When you start moving, that must be why. When you start moving, things start to shrink. And time starts moving differently. And that's why. So he made two postulates. He said, laws of the physics remains the same, and wherever you are, and the speed of light is constant. And that's it. So now you have a very good understanding of the theory of relativity. The problem is that that's actually in my mind, it's a very kind of nebulous concept, and it leads to a lot of paradoxes. I think everyone has heard about the twin paradox. No? Well, if the time changes, the real meaning of the twin paradox, the different versions, but the real problem is that if time changes when you move, and you have two people, two twin brothers, going towards each other. Which one is older than the other? One I prefer to twin paradox, which is not as famous but I like, is if it is the case that you have the size of things change as you gain speed. Let's do the following experiment. You dig a hole into a sheet of paper or metal. You take the hole out, and you start moving the two of them together. Now, from the point of view of each of them, the other one looks smaller. So the question is, will it go through? Won't it go through? So that's one of the paradoxes that that the theory of relativity kind of puts forth, and it's not quite easy to answer with a lot of mathematics that basically I think no one understands. So what we did is we looked at it again and thought in this book, maybe there's a simpler theory. Quoting a great physicist, may go to the simplest theory but no simpler, and we put our minds and thought about it, and this is really my father who came up with it. He thought, well, maybe we'll go back to the ether, and maybe there's something to it. Maybe there is a medium that we forgot about it, and maybe something that's everywhere that we don't think about. And going back a bit to Spinoza and what space is, maybe matter itself is what moves, what allows everything to move, what allows light to move. Maybe it's the vibration of the electrons that allows this movement. Just as in air, you have in a wave or sound, you actually have particles hitting each other and making things move. Maybe it's the same thing with light, but rather than having particles, you have electrons moving. And if that's the case, then we do have an ether all around us, and we can explain such phenomena. And if you want to really redo Michelson experiment, you could. You'd have to go in space where you actually don't have the air and the electrons following you, and you could remeasure the speed of light there. So there's ways that we could test our theory, but it's actually quite, I think, an interesting one, much simpler, and it can explain many things. It can actually explain one of the big items that was given as a fundamental proof of the general theory of relativity. So general has to do more with mass, and the special one has to do more with time and space and speed. So one of the big proof of the general one is that we looked at light that was going next to very dense stars and they curved, and our explanation for it is like, well, actually, do you know that when the sun sets, when you see the sunset, it's actually under the horizon, but it's already set. But because of the different densities of the atmosphere around you, light is bent, and we see it. You don't need relativity for it. And our idea is that is one thing that could that's our theory, is that we could explain what proved the light bending. So that's the gist of it. Unless people want me to go on and talk about math, but I think I'm trying to lose some people. But I'll close on the type of things that really excite me, and that's been it's very inspiring. The ability of people to change the world and to change things and to define things via their brain, which is something that we can all do, and being disruptive, which I think is something at Xaxis we do very much. So any question or anything I can tell someone? Yes?
So what did your father call it, the relativistic mythology?
Because the theory of relativity, I think, has become kind of like this myth. I think physics, or even though it's very simple, is seen is so close to what we are that it's really seen as something left for almost like the gods. And the physicists are oftentimes seen like the priests that are unattainable. That's something you see, in every day. Now, it's not the fault of the physicists themselves. When you meet them, they're very simple. Einstein would never have wanted that type of things, for example. But the theories of physics have taken the place of the mythology. And in many cases, and particularly in the relativity one, it's clear. With the atom bomb basically put an end to any kind of rational discussion or critique of it, or looking at you're an atom bomb denier, and it also gave the fear of God into people about it. So he views the theory of relativity, which is one theory that, like all scientific theory, can be expanded and refined, as having taken the status of mythology.
Shall we break it?
Yeah, so that's the idea, is to break it, yeah.
Can you tell us the actual twin paradox?
The actual twin paradox? Yeah, so the twin paradox, as it's usually put forth, is you have someone on Earth, and his twin brother takes a long, long trip to the stars, right? And the twin brother takes and is able to attain, once he's out of the Earth atmosphere, the twin brother is able to attain a very, very quick, very high speed. Would rather have it be a twin sister. So twin sister is able to attain very, very, very high speed. Such high speed gets close to the speed of light. And at moment, as it gets close to the speed of light, the time starts going more slowly for a person as opposed to someone on Earth. So the sister has a trip, lands on the foreign planet, collects some sample, and then does the trip in reverse. And when the sister comes back, sees her twin, who's now much, much older than her. So they're twins, but they have now the different age because time has moved at a different pace for them. And the reason time, in Einstein theory, the reason why time has moved at a different space is that, well, the laws of physics kind of are the same, but everything changes to make to keep the speed of light constant. So as you move forth, distances starts to contract and time starts to expand. So that's how it's said usually. My view of it is, if you really believe Einstein's relativity theory, there is no such thing as a frame of reference. It's not like you have the ether or something through which you can say, well, I'm moving fast or I'm moving slowly. Actually, each of them, looking at each other, would look at it like, oh my God, he's going so fast. Time must be going slower for the other person. And so the paradox would be, the real paradox is that if you accept that, when they come back together, they're each older than the other.
So do cells like degenerate at a slower rate if they're moving faster? Like the brother that's on the ship that's moving fast? Or his
Right,
gonna
yes.
break
So
down at a slower rate?
I don't believe in that, but yes.
Okay, that's what you're saying.
Yes. If you're now, the interpretation of the slowing time can differ a bit, but the idea is that yes, you have a clock, your cell, as you move faster, as opposed to someone else, your clock starts going slower and slower.
Yeah.
So compared to the other person, you are moving slower. Now, but your vision of time, the cell's vision of time, is still the same. As in, like, it's not like 3 minutes has passed for you, but you only grew older in 2 minutes. Mm-hmm. It's like 3 minutes has passed for you, 2 hours has passed for them. Now, you don't see that if for this effect to be seen, you have to be pretty close to, or measured, you have to be pretty close to the speed of light. Typically, relativistic theories, at least you can see them in numbers, when you get to 0.14 of the speed of light. That's what the number was given in school. Now, people claim that with very precise atomic clocks, you can measure that difference. They're so precise that you can see little differences at slower speed, and that you can see them in just orbiting around the Earth. But yeah, I haven't seen evidence of that. But yeah.
How do you apply your passion for physics to like your day-to-day stuff, like from soccer to work to raising a family?
Well, I think it's more I apply it more as the process what I take most of it is more, it's not so much the experiments and stuff, but as the process. So you see how things behave, you model the world, and then verify that model. And that's something we do every day in engineering. And that's how I try to think of things when it comes to even in politics, like, okay, how does it really work? And that's how I would do it. Now for kids, with the family, I try to I try to a bit do some experiments, but I think I'm waiting a bit until they're a bit older to not bore them to death. But that's how I view it. And in addition, I also take it in as far as politics and day-to-day. I take the fact that changing people's perception and changing things is available to everyone. That I take very to heart. So I think that you can. I'm a big believer in like the democracy and the people thinking, and basically the smarts from bottom rather from the ups. Going back to your inspiration.
Thank you.
Do you keep up to date on developments in modern physics at all? Is there anything interesting that people are working on?
No, honestly, I haven't in the past couple of years. The book was done a couple of years ago. I haven't done too much in a couple of years. I looked at it last 10 years ago, but no, I haven't really. There's always interesting stuff going on. I don't follow it very, very closely, actually. What did I find that was very interesting? There were some things that we talked about where there's a lot of kind of false hope or false things. There were talks about having found that the neutrinos were breaking the speed of light, but that actually ended up not being accurate. The particle creation is also kind of interesting, but no, I can't say I've been following it very, very deeply anymore. That's the problem with scientists, actually, as opposed to artists and things like that, is that, I did a CD-ROM, I worked on the book, and okay, it's good theory now, we don't want to touch it a little bit. It's probably time for me to revisit it and go back there.
Did you like butt heads a lot with your father growing up over physics, or did you kind of were aligned with his thinking? Or?
Oh, no. So growing up, not so much, no, because it's just something. It was hard to understand. He'd talk about it. He was very, very into it, so I didn't understand much. No. But when we started doing that, I think a lot of it was, he would explain things. I butt head with him a bit. He had some very interesting theories. So on the black hole, for example. And this is something where I came from school and trying to apply my knowledge. And he believed, for example, that black holes are just as matter is what the ether is, and black holes in his mind is not the condensed matter, but is actually the lack of matter. So it's like when you don't see something, it's because there's nothing to there's nothing. Exactly. You turn off the light, it's dark. And he had also interesting theories as to the existence of positively charged. He thought that there's no such thing, that just the electron and the positive charge is just missing things, something just because you removed an electron, and so that type of things was but head on him on that. It seems so kind of different thinking. That was more when I got older. In the beginning, on the contrary, it was like when I went to him and talked about like this theory of relativity, and I was like, it's just strange. So that's actually was more positive rewarding. I was asking him, well, okay, mass increases. So as mass increases to infinity, does gravity increase and things starting to that type of things? And he was like, no, I don't actually. I don't believe that mass increase. And we go over there into why proposing alternative explanation, going from the experiment that makes us think that mass increase to the explanation. So actually it tended to be more in the beginning very kind of positive, as in like I have doubts, and he's like, well, that's interesting, let's think about it. And then when he went into his like big theories, I was like, that's weird. And that's when I had headbutt and he could laugh. questions? Yeah.
Yeah, I mean, Einstein famously, when he proposed special relativity, he called an experiment, the Eclipse. You know, we'll go observe the star, and if it warps, as you explained, there's like a
Yeah.
theory. Do you have you like in your book like proposed like the definitive experiment that would prove or break the theory?
Oh yeah.
Because
So
that's the element.
there's a couple. I think you could reconduct Michelson theory in space, and that would do it. You could go. That would be one way. Yeah. Basically, our idea is that if matter. It's true that if matter isn't the one that propagate electrons aren't the one that propagate things, then you should be able to see a difference in the speed of light as you perceive it once you're outside. Once you don't have the air coming and carrying with you, and it's going kind of against
Do you need to be out of the gravity field, or do you have a deep well, or do you just need to be?
No. I think you just need to be. So I think we're looking at it at how fast you'd have to go, and I think you'd be able to do it with rotating the Earth. Where you actually have enough atmosphere that you would kind of go to carry and to have enough kind of particles to measure. So I think it'd be enough. Otherwise, it'll be when we're able to attain speeds that are so high that you'll be thinking. But that's one experiment. That's the big one that we think about. Yeah. We go against it with another one in there. I don't remember which one we thought about. But that's the big one that I came up with. All right. Well, thank you very much.